Thank you.
Thank you very much. Thank you, Chairman.
Thank you.
And first of all, I'd like to thank the organizers for inviting me to this press conference. And I've changed my title slightly, and the updated title is Electron Fractionalization and Cuprate Superconductivity. The outline of my talk is the following. The main subject of my talk is how does physics of electron fractionalization work for cuprates. So in the first part, I'm going to talk about some initial calculation results for cuprates. And based on that results, some insight was gained, and that is electron bistability and picture of fractionalization. Then the fractionalization has many consequences in experimental results. And in the first part, I'm going to talk about the self-energy structure of the quasi particle when the fractionalization is taking place. In the second part, I'm going to talk about the prediction for the resonant inelastic X-ray scattering if the fractionalization occurs. And in the third part, the TC scaling based on the fractionalization will be discussed. And then the summary will follow. In the first part, I'm going to talk about ab initio calculation based on MACE, which is multi-scale ab initio scheme for correlated electrons, which was developed for decades in our group, and that is a powerful method to study strongly electron correlated systems, particularly high TC superconductors with high accuracy. Now, by using our developed method, we have derived the ab initio Hamiltonian for the cuprate without any adjustable parameters, and then we have solved by using quantum many-body solvent. In the case of Lacan to kappa 04, we have reproduced the Mott gap of the size of 2 electron volt, which was reported a long time ago here in the optical conductivity, where the Mott gap or charge gap is 2 electron volt, and we have reproduced. The antiferrometer orbital moment in mother material is 0.6 Bohr magnitude, which is also reported a long time ago, and we have reproduced that. These are the first quantitative reproduction of these values without any adjustable parameters. Now, if the carriers are doped, then we found the dominant superconducting phase for the mercury-based compounds, and it also shows very severe competition with the charge order. And indeed, around 10% dope booking, we find that the lowest and the true ground state is charge for spin 8 period strike, which is in agreement with experimental indication of mercury compounds. Beyond that carrier concentration, we see the superconducting state is the true ground state, but the energy difference is tiny, the order of 50 Kelvin. In any case, we have reproduced the cuprate phase without adjustable parameters. So we have reached now firm basis. So it's now time to discuss the physics based on this ab initio calculations. The first part we would like to point out is the electron bistability and the picture of fractionalization. If you see the case of the simplified Hamiltonians, apart from the ab initio Hamiltonian, for instance, in the case of the simple Hubbard model or the ab initio Hamiltonian of cuprates, by switching off the long-range part of Coulomb interaction. And then what we see basically, the energy as a function of carrier concentration shows concave curve with negative curvature, which means that some electronic instability between these 2 points. And indeed, this concave curve is coming from the concave curve of the kinetic energy, and that is the consequence of the motifs. In the motif theta, the carriers are localized and confined. However, upon carrier doping, that carrier becomes released and becomes quickly coherent, and that makes the nonlinear reduction of the kinetic energy. That is the reason of this concave curve. And if you expand the energy as a function of doping concentration, it shows negative curvature. That means quadratic term coefficient B is negative. And if B is negative, because delta square term is effective carrier-carrier interaction. So this leads to the effective attraction, which is very strong. And it also leads to the charge instability because of negative curvature. It is thermodynamically unstable in this region, and the system goes into the phase separation of this and that. By the way, I forgot to say that this phase diagram is obtained when we impose the charge homogeneity. And as I mentioned in the previous slide, in the case of mercury compound, we have charge order, but in this case we have imposed the charge uniformity, and that we can extract the essence of the physics which is coming from motifs. Now, if we have such a kind of double well type structure in the energy, then it also introduces the bistable excitation. One is stable in this region, and the other is stable in the other region. And in the low doping region, we find some hidden fermion excitation because of this stability, and we call that dark fermion. And in the overdoped region, we have a conventional quasar particle, and because we have a quantum tandem between C and D for these stable excitations, we have a C dagger D or D dagger C term in the second quantized formulation. So, because of this bistability, the electron is fractionalized into quasar particle part and dark fermion part. And the simplest effective Hamiltonian to describe this physics is a two-component fermion system where the conventional quasar particle and the dark fermions are hybridizing each other through the hybridization term lambda. Now, let me discuss some consequences of this fractionalization. And in the first part, I'm going to talk about self-energy. And if we solve this two-component fermion systems, which is two-component non-interacting system, so we can easily solve it. And the quasar particle grid function as a structure with a self-energy, sigma normal, which is given by the pole of the original d-fermion dispersion. So, because it is a pole, the normal self-energy diverges at this energy. This means that the grid function becomes zero. And because of that, we have a gap structure in the spectral function, and it is interpreted as a pseudo-gap. Now, what happens in the superconducting state? In the superconducting state, we can again solve this Hamiltonian, and the green function is given by this form, where the self-energy is given by the contribution of the original normal self-energy part and the contribution from the pairing. A normal self-energy enters in this W function. Now, if we take some appropriate parameters for epsilon, lambda, and delta, then we can calculate the spectral function, imaginary part of the Green's function, and this shows somewhat peak, deep, and half structure in the negative energy side. And we can also calculate the self-energy, the normal self-energy, the imaginary part, as a prominent peak structure because we have a pole here at epsilon d. And W function also has a pole whose energy is is exactly the same as epsilon d here. And then if you calculate W function in the imaginary part, it also shows the peak structure. And if you calculate the sum of these two, sigma normal plus W, which appears in the grid function, then we find no peak structure in that energy. So the prominent peaks appear if fractionalization is taking place in the normal as well as abnormal self energy in the imaginary part, and their cancellation in the spectral function is a very remarkable property of the fractionalization, and this can be evidence for the fractionalization. Now let me go on to the real experimental data. This is the data taken by Takeshi Konda and his company 10 years ago for the bismuth 2212 optimal box case of TC 90 Kelvin. Now in this case, as I mentioned, there is a famous big, deep, and hump structure, and we can fit this big, deep hump structure by taking the two-component fermion model in the superconducting state. And as I have shown already in the previous slide, we can reproduce the structure of the big, deep hump more or less quantitatively with the same energy position of the peaks. Now, because the artist can measure only the negative energy side, I'm showing the negative energy side only. And starting from this experimental result, apart from the theoretical analysis, we have analyzed this artist data without any theoretical assumption, just by using Boltzmann machine learning, and we extracted the normal and the abnormal self energy from this spectral function separately by thanks to the Boltzmann machine learning. And then what we found is that there's a prominent peak in the normal and abnormal self energy at the energy scale of 0.07 electron volt. And if we calculate the normal self energy and abnormal contribution to the W function, we again reproduce the prominent peak structure, and if we sum up them, we have the disappearance of the peak structure in the summation. So, two-component fermion model analysis, and also the machine learning analysis without any theoretical assumption shows quite good agreement. And normal self energy has a peak structure, negative peak structure, and W function has a positive peak structure, and their summation shows the suppression of the peak. So these analyses support the fractionalization coming from the Argus data. Now, why is that peak important? Because the superconducting order parameter, which is given by the real part of the gap normal self energy at zero frequency, and that's the superconducting order parameter can be given by the imaginary part of the normal self energy through the Kramers-Kronis transformation. Now, by using this Kramers-Kronis transformation, we can estimate the contribution of the imaginary part of the abnormal self energy, which we found here, to the real part of the abnormal self energy by taking the increment function or truncated Kramers-Kronis transformation, and we find a very steep increase, which means that this peak intensity is giving was 90% of the gap size. So this means that the dark fermion generating the self-energy peak is the origin of the high DC, and it holds the key to understand high DC. Now, let me go on to the prediction for the RIGS. RIGS is following is given by this process. First, irradiation of the X-ray excites the core electron to to the conduction electron, and then a quark hole is created. Then near the Fermi energy, we have one electron, additional one electron, and we can trace the one electron dynamics. After some period, the quark hole lifetime comes in, and then the valence electron decays into the quark hole, and then it's filled. Now we have particle hole exciton, and we can trace the exciton dynamics. Now, in the formula, we can give the intensity of the Rick spectrum, and the one electron dynamics is given in this part where the quark hole lifetime enters as a gamma. Inverse of the quark hole time is gamma. If we have an exciton lifetime, then we also have another lifetime eta, and by solving this formula, then we can get understand the exciton dynamics as well as single electron dynamics. In the cuprate, we can utilize kappa L3H as well as oxygen KH for the charge excitation without any spin flipping. And in the case of kappa L3H, gamma is the order of 0.3 electron volt, while oxygen KH is much smaller. So depending on that, we can separate the contribution of exciton dynamics and the quark hole one electron dynamics. Now, we have solved that Rick's intensity formula by using the two-component fermion system model. And then what we find is that the exciton peak found near the one electron volt is enhanced when in the superconducting state as compared to the pseudo phase, normal phase. The physics of the enhancement is the following. First, the exciton is created predominantly for this peak between the electron excitation in the in-gap state around pi position and the antinodal point, hole creation around the antinodal point. And this exciton pair is giving a predominant contribution to this peak. Now, in the pseudo-gap phase, because of fractionalization, substantial part of the hole or electron in the antinodal region belongs to the dark fermion site, which is hidden in the Rick's intensity. In the superconducting state, however, this substantial dark fermion component is suppressed, and the normal component, quasi-particle component, is recovered. And because of that, the exciton dynamics can be detected by the Rick's intensity. So this is the reason why we have a substantial enhancement. And this is very unique properties of the electron fractionalization. So if it is enhanced in experiment, it gives us the strong support for the fractionation, particularly around the antinodal point. And indeed, if we take the single band case without any fractionalization, then we don't see any enhancement for the exciton peak. Now, let me go on to the TC scaling. And what determined TC, which was first discussed long time ago in sort of Wemler plot or Holmes plot. And actually, in that case, TC is scaled by the superfluid density, or in my terminology, the superconducting order parameters, the average of C dagger. And however, of course, this gives you somehow more or less a rough estimate of the TC, because it shows very rough linearity between TC and F here. However, based on the fractalization, we can propose better scaling by taking the amplitude of the W function peak. That is a contribution from the anomalous component of the self-energy. And indeed, the intensity of this function in the imaginary part gives you the attractive interaction, as is well known in the Eliashberg formalism. And the product of this G and F is just a mean field, because this is the sort of mean field order parameter, and this is attractive interaction. So this is the true mean field which is acting on the electrons. This two parameter scaling is not enough, and we find that gamma term also enters in the scaling of TC. The gamma term means the omega linear component of the imaginary part of the sigma normal. Sigma normal self-energy indeed shows more or less omega linear scaling, as in the case of marginal Fermi-Leggett, and the C1 term is proportional to this gamma. So it's really counterintuitive, because the electron dissipation becomes larger than the TC is enhanced. However, this can be understood by the following fact. The gamma represents the degree of quantum entanglement, and for the Cooper pairing, that kind of quantum entanglement is important, and that entanglement also damages the normal electron transport, and that is the origin of the marginal Fermi-Leggett. And this term of linearity is also related to the Planckian dissipation proposed by Sachdev and Zarnem. Now, by taking these scaling, we can have much better scaling between TC and these parameters. Now, yesterday, Ivan Vozovich was talking about the TC scaling as a function of the superfluid density, which shows some sublinear behavior, both in the underdoped and overdoped side. In the part of the underdoped part, we can explain why it has sublinearity. If TC is proportional to F, superfluid density, then it should be more or less linear. However, gamma becomes large and gamma becomes divergent when the carrier concentration becomes the high stability of electron coming from the mottness, and that generates the fractionalization of electrons into C and D. Fractionalization generates remarkable structure of self-energy. First, peak emergence in the normal and the anomalous part, and their cancellation, complete cancellation between these two. And the peak of the anomalous part is the origin of the high TC. Now, fractionation theory also predicts the enhanced Rix intensity in the superconducting phase in the energy range of 1 electron volt. And it is very unusual, because the superconducting gap size is below the 0.1 electron volt. However, the enhancement is observed in the energy scale of 1 electron volt or beyond. Now, fractionalization theory offers better scaling of TC beyond the Uemura plot, Holmes plot, and others. Now, to get more better understanding of strongly correlated electron systems, we need to go further to the integrated spectroscopy by combining ARPES, tunneling, X-ray, neutron, and others. And we have proposed just the combination of photo emission analysis and Rix, yes. Combination of these two predicted the enhancement of Rix intensity in the superconducting state. And if we combine all of them, we can reach much more better understanding in the future. Thank you very much for your attention.
Thank you.
So thanks, Professor Imada, for a very nice talk. Just for clarification, what you call fractionalization is reading for your paper. I was calling hidden fermion theory. Would you agree with it? And second following question, the hidden fermion, could it be the scattered electron by charge density wave?
I know your interpretation, and first, the fractionalization means that the fractionalization into quasar particle and the hidden fermion or dark fermion. And in the second question, the fractionalization, as I mentioned, is coming from the bistable structure of the energy, and that is coming from the modulus. That has nothing to do with charge density wave or charge order, in my interpretation. I know your interpretation, but my interpretation is
there is a paper by Shiro Sakai where they say that the hidden fermion is the antiferromagnetically scattered fermion. So
no.
You are maybe part of this paper, actually.
In any case, hidden fermion is found in the paramagnetic phase where the DMFT doesn't introduce any substantial antiferromagnetic fluctuations, even though we have found the hidden fermion. So It's purely coming from the modulus.